Learning Outcome 8.7. Draw a block diagram for frequency division multiplexing and demultiplexing. With Learning Outcome 8.6, determine the spectrum for all signals in an amplitude modulation process. And Learning Outcome 8.8, calculate constraints on signal spectra to be able to reconstruct an amplitude modulated signal. How many of you can recognize what this is? You don't see them very often today. It's the front plate for an old-fashioned analog radio receiver, showing all the frequencies of radio stations, and you can tune between them. Well, we've only been talking about modulating with one frequency. And how do we get all those multiple radio stations out there to share the airwaves together? We're going to talk about that in this outcome. This is frequency division multiplexing, where we're going to put multiple radio stations separated by frequency into the atmosphere or any other medium. We've been talking about the case where we have a signal which has a spectrum, we add a constant, we modulate it, and now we have a spectrum that's ready to go. Now we're going to talk about a second signal. This will have a different spectrum. We're going to consider that it is also band limited with the same bandwidth. We'll again add a constant and then modulate it, but instead of modulating at a frequency omega 1, we'll modulate at a frequency omega 2, and it will therefore determine a different spectrum. What we want to do now is send this spectrum as well as this spectrum together out in the airwaves. So we'll just simply add the two of them. And if we did it right, we will set things up so that this spectrum will not interfere with this spectrum, and everything shares nicely. This is the process called multiplexing, specifically frequency division multiplexing. Look at our variable, it's frequency. We're putting multiple signals in frequency. So now let's take a look at this a little bit closer. What are the constraints to make this work? Let's in particular look at these two. Omega 1 plus omega m is a frequency here. Omega 2 minus omega m is a frequency here. These guys will not interfere if omega 1 plus omega m is to the left or less than omega 2 minus omega m. You do some algebra. So long as the distance between these two carrier frequencies is greater than the total bandwidth each shares, then we'll be okay and they will not interfere. This is what agencies, like in America, the Federal Communications Commission, FCC, do to make sure that everybody can share. They tell everybody what the maximum frequency that they're allowed to transmit is, how wide of a spectrum their signal can have, and your radio station will achieve that by passing the original signal through a low-pass filter. And then they tell everybody what frequency you can transmit at and what the range of frequencies is that you may encompass, what your bandwidth is. And companies pay big money for this. So once we've generated this, this is transmitted, propagates, and then someplace we receive our signal. On your car radio, in your home stereo, whatever you're using. And then depending on what we want to do with it, we make multiple copies of it. And by using a band-pass filter, we will separate out just the part of the signal that we care about. And somebody else, or if you're listening to a different channel at a different time, will use a different band-pass filter to extract the other signal. These are then processed the way we've discussed in previous videos to do the demodulation. This part of the process we call multiplexing, putting multiple signals within a given frequency band. This part of the process is what we call demultiplexing, separating everything back out. So let's review. We start off with two different signals we want to transmit. One will be transmitted at frequency omega 1, one will be at frequency omega 2. That's the modulation part of the process. We then combine them in a step called multiplexing, transmit them, receive them, then choose your radio channel and demultiplex. Then we demodulate to get our original signal back. What type of demodulation is this? Notice we've got a cosine omega 1t, cosine omega 1t, the same frequency, same phase. This is synchronous demodulation. Because of that, we did not have to do any pre-treatments to our signal. Okay, the other case, we take our original signal, we add our amplitude, then we modulate. Adding of A guarantees we have a signal that is totally positive. That's a process called modulation. Again, combining them is multiplexing. We transmit, we receive, we demultiplex by choosing our radio channel. Then we do demodulation by passing our signal through a full wave rectifier and then a low pass filter. What type of demodulation is this? This is asynchronous demodulation. That's why we had to have the addition of a constant at the beginning. You should make sure that for each of these processes, you can start with a given signal in a given spectrum, choose values for each of the parameters, and draw usually the time domain, but also the frequency domain signal that accompanies them.